Ah. I'm not sure. Uh-oh. Let's see. Sorry, guys. All right. All right. Has anybody been in a classroom where they're using this? I just want to be able to take notes so that you guys so we can say things for you guys later. Oh, how about now? That's better. You know what I mean? Oh. Better? Hey, I just turned the volume down just in case, you know, this happens in one of your other classes to another teacher. Okay, so everybody can hear me? Those of you online, can everybody hear me? Awesome. Cool. All right, so we're gonna finish up chapter 2, doing 2.4 and 2.5, second derivative and marginal cost. So it says, since the derivative is itself a function, we can calculate its derivative. So like derivative of the derivative. And the reason why, I can scroll down here a little bit. Passes the vertical line test, right? So we know that the derivative is a function because it passes the vertical line test. Okay, and we can write it, the second derivative, like f prime prime. It can also be written, and we talked a little bit about, boy, I forgot my mouse. This is going to be interesting. There we go. We talked about Leibniz notation before. So in Leibniz notation, just like you would do in the first derivative, instead of no numbers, you're going to end up with a 2. So it looks something like this. Oops. It looks like d2y over dx2. Okay, now a couple lessons ago, and that's why I'm saying recall, that the derivative of a function tells us whether the function is increasing or decreasing, right? So if what they're saying here is if the derivative is greater than 0, that means it's above the x-axis. Okay, so you might want to note that. Or if it's below the x-axis. So I'm going to say this is above and this is below the x-axis. So they're saying, and I want to get blue here. They're saying that if the derivative, and the derivative in this drawing is the blue diagram, if the derivative is above, like it is right here, right? If this is above the x-axis on some interval, then f of x, or the original function, which is the red function here, f of x, is increasing on that interval. Now, if you look at that interval from -1 to 0, so what they're saying there, if we do our own little intervals here. So you can do another interval right through here. There, so you should have 3 lines there. So notice that what we got going on here is when the derivative is above the x-axis, the original function is increasing, right? And when it's below the x-axis, like for example, over here, right? Then it says that the original function f would be decreasing on that interval. A little bit about how the graphs relate to each other, the function and the derivative. So just to kind of summarize what we just did here, I'm going to say that the derivative, f prime of x, is below the x-axis when the original function is decreasing. And f prime of x is above x-axis when f of x is increasing. So it's just kind of, you could go either way with it. So we did this in a prior lesson. So now we're going to take a look at, well, what about the second derivative? How does it relate to the original function and to the first derivative? Okay. Everybody ready? So again, we have so let's draw in our intervals. So let's see, where do things change? Let's draw in one at straight through, oh, I don't want to use that pen. So we'll do a line straight through there. Go to the top of the blue graph and do a line straight down through there. There's another little interval change there in the middle, and one right where the green, the second derivative, crosses the x-axis. So let's take a look at what happens when the second derivative is above the x-axis. So that would be here and here. So if the second derivative is above the x-axis on a certain interval, and do I need to draw in another interval? No, that's all of them. Okay, so when the second derivative is above the x-axis, then the first derivative will be increasing on that interval. So notice that the blue second derivative is increasing, right? On the same interval that the second derivative is above the x-axis. Does that make sense? Okay, and then let's look at on the bottom here. Let me use a darker green. Now notice here, the second derivative is below the x-axis, okay? And notice that on that interval, on that whole interval, the blue derivative graph is decreasing, right? So it's decreasing over that entire interval, right? From there to there, increasing or decreasing over the whole interval. So that's what it's saying there. So to put it the other way around also, we can say that f double prime of x, or you can even just say f double prime. You know, the book kind of goes back and forth with that notation, so I'll use it sort of interchangeably. You could say that it is below x-axis when f prime of x is what? Increasing or decreasing?
Decreasing.
Prime must be decreasing. And I'm just saying the same thing that they are, just kind of backwards. So you get used to reading it both ways, okay? All right, and then we can do when f double prime of x is above the x-axis, then f prime of x is doing what?
Increasing.
Oven chicken hairs.
Okay. Now you guys remember concavity, right? Whether so if I'm drawing a U, is that concave up or concave down? Concave up, right? And then if I'm drawing an upside down U, then it's concave down. So let's talk about concavity and how it can also be a clue as to what's happening on the graph. Okay. So first thing if f double prime is above the x-axis, right, greater than 0 on an interval, then f prime is increasing and f is concave up, right? Now, notice too that always, this is always true. Let's see, if this is above the x-axis, then f is concave up. That's what I want you to glean from that information. Then if it's below the x-axis, then the original function will always be concave down. Now you can't necessarily say exactly what All right, so let's go to this. Okay, so for here, so this is concave up, right? Concave up. Everywhere. So according to this, if f prime is concave up everywhere, then it's going to be, well, the direction said, decide where the second derivatives are positive and where they are negative. Well, in the whole graph, this is all concave up, right? So you can say that f prime double prime remember, where, question is, where are they positive and where are they negative? So f double prime is concave everywhere on this whole graph, therefore it is positive everywhere. And if you want to know is this concave up or concave down? Down. Is it ever concave up? It is not. Therefore, you can say, well, we should write this first. This is concave. So you can say g double prime of x is less than 0 everywhere. Okay. So this one we already decided is so let's see, we could say h of x is concave down when x is what? Negative, right? When x is negative, or we can say less than 0. So we can say that h double prime of x is less than 0 when x is less than 0. And also h, oops. It's concave up when x is greater than 0. So h double prime of x is greater than 0 when x is greater than 0. When I taught this class, I gave an extra credit assignment. This extra credit assignment talks about, is fascinating, talks about the coronavirus and how it the video came out when coronavirus. I'll put that on, gosh, I'm on so many different learning platforms. You guys are Moodle, right? Okay. All right. Okay, so here's an example. Population is growing in a confined environment, often follows a logistical growth curve. So we're confined, right? We're confined on Earth, right? So that's why it is. Wait till you see the video. It's really very interesting. Describe how the rate at which the population is increasing changes over time. What is the sign of the second derivative? And remember, this is just Leibniz notation. We're really just asking for f double prime. And then it says, what is the practical interpretation of t and L? Okay, so let's put the whole graph up here. Oops. All right, so let's describe what's going on. From 0 to that T star, concave up, concave down. So if I went, from here to here. Yeah, concave up, right? So in that interval, this is concave up. So we know that the second derivative is going to be above the x-axis or below. Above, very good, yeah. All right, what else is going? Oh, and then we've got something else happening here. Concave up or concave down? Down, right? Therefore, we know that the second derivative is going to be below the x-axis, right? And they always say that by saying less than 0, okay? And another good way to Okay, what else do we want to know about this? Oh, this is important. Now this is gonna come up in a big way in another section coming up. What's happening here is in this interval right here, we're increasing at a different rate. And then up here, which is really interesting, is it is increasing there too, right? So right here, we are still increasing, but at a decreasing rate. What else do I want you to know about this graph? Let's see. There's a certain point on this graph right here where it changes. And that's called the inflection point. And that is the point where the second derivative is actually equal to 0. And technically, this is the point where a graph hits a max rate. And you could say like a max rate of increasing. All right, what else do I want you to know? There's a name for this guy up here. What's this called? You guys remember from math in high school? Yeah, so that's a horizontal asymptote. And what it shows is that that means it is reaching its carrying capacity. Usually these are used for population. models, but obviously the number of cases is the same kind of thing as the number of people, right? Shows that population is reaching carrying capacity. Oh, I see. Some of you guys are on your computers back there, so you can see better. That was very smart of you to bring your computer. Because I was looking like, good idea, guys. You're welcome to do that next time if whatever. But I guess some of this is close for some of you, but not so much in the back. So, all right. Now what else? Oh, I don't want you to think that. Oops. I'm just going to make a little side graph here. Or you could have a graph that has an inflection point that goes from concave down to concave up. So that could happen too, right? So it doesn't just happen at the. All right, any questions on anything on that graph? I gave you a lot. Everybody ready? Okay. Okay, so here's an example. The table shows the number of abortions per year in thousands reported by the US in the year. So we've got 1972 all the way through 2013. So the first question here is calculate the average rate of change for the time interval shown between 1972 and 2013. Well, the average rate of change, if you guys remember from the last lesson, change is that little triangle symbol, is going to equal to the change in A, for abortions, over the change in time. Okay, so we're going to take 1,034 and subtract 587. So 1,034 minus 587 over 1975 minus 1972. Just slope, right? And if you do that, you will get 447 over 3, which is equal to 149. So let's say average rate of change, which really is just the derivative at a particular point, right? All right, so then I would put 149 here. And if I continue to do that for all the subsequent points, I would get these numbers. 104, 7, 4, negative 50, negative 9.2. Oops, let me write that legibly. Negative 21.4, negative 42, and negative 343. So okay, so that's answer A. Now they want you to look at kind of trends. So what about the sign of the what do you think about the sign during period 1972 to 1995? Now let me tell you what that period is on the graph here. So first of all, is it increasing or decreasing? So let's say something about that. We can say that we're decreasing here. And then according to our other rules, we can say that since average rate of change is decreasing, so then we know that the second derivative, since the first derivative is decreasing, then we know for sure, remember back to the graphs from before, then we know for sure that the second derivative is going to be above or below the x-axis. Let's go back. So again, average rate of change is decreasing. So the derivative is decreasing, and we want to know what's going on with the second derivative. This diagram right here, use that, okay? It'll be very helpful when you're answering questions. Okay. So since the average rate of change, our first derivative, is decreasing, we know that the second derivative must be below the x-axis, okay? So, oops. So we know the second derivative is less than 0, or you can say below the x-axis. And then this is just a graph to show you what's going on. Notice this is concave down. And remember, if it's concave down, the second derivative back from this diagram here, right? If it's concave down, okay? So use the graphs and the rules sort of interchangeably and get used to it because it's not going away. This description is important. So from in that interval, notice from 0 to, or from 75 to 1995 is concave down, and the second derivative would be below the x-axis. Now remember, this is not the second derivative. All right. That was section 2.4. Now we're going to do section 2.5, which is marginal cost and revenue. So think about a linear graph.
Professor, every time you step away, we can't hear you.
Okay, sorry. That's the trials and tribulations of trying to teach from a classroom and online. So I will try and work with that. Do you guys have any questions?
Yeah, a lot, actually.
Can you ask one?
Can I just talk to you after class?
Yeah, that sounds fine. And actually, will you give me time to get home? We can meet later.
I actually have a class right after this.
Oh, okay.
5 minutes in between.
Okay, well, we'll set up a time, all right, bud?
That's fine.
Okay, I'll try and stay in front of my computer. That's hard for me to do, but I'll try. Okay, so let's say this equation that we just did is, let's say it's y equals 2x plus, I don't know, 3. So what really is going on is we're going, this is slope, right? So we're going rise over run to get to our next point, right? The thing about a linear equation is that you go up the same amount, you're going to go over the same amount, right? So the slope is constant. Sorry, guys. I told you I wasn't going to do that. All right. So this is the y-intercept at 3, right? And you're going to go up 2 over 1, up 2 over 1. So the 3 is the initial value. So let's say it costs $3 already before you even start making things, right? Because you have to pay people or you have to pay for your office. But then every item that you make, you're going to make $2 off every item you sell, right? So when I say marginal cost or marginal profit, I mean slope. And I mean, slope is the derivative, right? So keep that in mind. Think to yourself, if they're saying marginal, think slope, think derivative, okay? All right. Okay, so now we're going to move on to marginal cost and revenue. So management decisions within a particular firm or industry usually depend on the cost and revenues involved, right? In this section, we're going to look at the cost and revenue functions. So suppose that you're running an airline, for example, and wonder if adding one more flight is going to make the airline money or not, right? So you would want to look at things like marginal cost and marginal revenue, right? How much money do I make for each new flight, right? And how much does it cost me for each new flight, right? You've got people to pay, right? You've got the flight attendants, you've got the pilots, you've got the co-pilots, right? There's cost involved with adding a new flight. Okay, so there's a simple enough formula. Marginal cost is simply the change in cost over the change in quantity. So look at it like this. The change in cost would be like you have a certain number of flights, let's say Q, and you want to add 1. And then you would subtract the cost of just producing Q. This is just slope, right? Y2 minus Y1, X2 minus X1, right? So then this would be whatever Q is plus 1 minus Q. So what you get there, of course, Q minus Q, that goes away. So you end up just with C Q plus 1 minus C Q over 1, right? Which of course is just equal to C of Q. And using the same sort of logic, we could do the same thing for marginal revenue. So it is going to be, well, we don't need to go through the whole thing, but it is going to be the same thing, only this time revenue of making some quantity plus 1 more minus revenue of what they used to make. Let me just write it somewhere else. Huh? Okay. All right, cool. What else did I want to tell you about that? Let's see. Okay, I think that's good. And just one more thing I want to say about that, and that is if the marginal revenue is greater than the marginal cost, and as long as the decision of creating one more flight is purely financial, sometimes it's not, right? Sometimes there's other factors besides making money involved. But if the marginal cost is greater than the marginal, sorry, if the marginal revenue is greater than the marginal cost, then yeah, you should add. Then they should add another flight. All right, now let's bring this idea home with a graph. Any questions so far? Okay. All right, so here's a graph. CQ and RQ, cost and revenue. And notice that these are not, this graph, CQ and RQ are not derivatives. They're the original functions, right? Like how much it costs to make a certain, or how much it costs to, we're talking about another flight. How much it costs to make another flight, how much money they make on another flight. Okay, so the actual slope at a particular time, and let's do something like this so you can visualize it on a graph. Say this is 100, okay? So if you look at that point instantaneously and that point instantaneously, then the slope at that point is that slope, right? Whereas the slope at the other point is that much. So what do you guys think? Is the red slope steeper or the blue slope? Which one is steeper? The blue one, definitely, right? Yeah. Okay, so let's note the slope of the revenue function is slope of the revenue function is marginal revenue. Okay, the slope of that is marginal revenue. And the slope of the cost function is marginal cost. So what can we say at Q equals 100? So if we decide right now we're making 100, and remember, we're trying to decide here, should we have 101 flights, right? So we're not going to look at 101, we're going to look at 100 and see what's going on at 100. So at Q equals 100, we can see that marginal revenue is greater than marginal cost. Meaning if you compare the slope of the red and the blue lines, the blue line is more, the slope is more, right? So marginal revenue would be the slope of the blue line is greater than the slope of the pink line. So based on that, and what I said earlier, if marginal cost is more than if marginal revenue is more than marginal cost, then yeah, you should go ahead and add another flight, right? So don't think that you have to look at 101. You're looking at 100. You're looking at Q at that particular point on the graph. If marginal revenue has a steeper slope than marginal cost, or I should say the slope of the function has a steeper than the slope of the other function, then you're good, right? You should, yeah, go ahead and do it. Okay. How are we doing online, people? Questions?
Nope.
Okay, I think you said no.
Good too.
Okay. All right, so now we're going to look at a graph. So remember, these are the function graphs, not the graph. So which is greater at Q2? So if we're talking about, I'm going to put, that's a little bit off. I'm going to put Q2, whoops, right there. So it says, which is greater at quantity 2? Marginal cost or marginal revenue? Well, the marginal revenue is the line. Marginal revenue, let me color code this here. Marginal revenue is the line. Marginal cost is the kind of curvy thing, okay? So is it marginal cost or marginal revenue? Well, what you need to do is you need to sketch in what the slope would be that's tangent to that very point that it goes through, right? So this is where it goes through the revenue, right? And then this one is the slope. Remember, we just want a slope that's tangent. Oops. And the way I've drawn it is really the way it is. The pink line is definitely steeper, right? So we can say that at this point right there for Q2, we can say that the marginal cost is bigger, right? I forgot A. Sorry, I didn't answer A. Okay, so we can say marginal cost is greater than marginal revenue, and that's because the slope of the pink line is steeper than the slope of the blue line. All right, so let's go back and answer A. So it says, if cost and revenue are given by the graph in the figure, for what quantities does the firm make a profit? So let's say that they make a profit when Q is in between two numbers. Any ideas? What two numbers will they be making a profit? When is marginal revenue bigger than marginal cost? Between what two numbers on the graph?
Between 130 and 215.
Yeah, absolutely. $130 and $215. Oh, I answered in the wrong place, sorry. Q is between 130 and 215. So back to point Q2. Is the company going to make a profit at Q2? Definitely not, right? Because the costs are bigger than the costs are more than the revenue. All right, now here's a good question. Should the company increase or decrease production at point Q1? Let's see here. Let me draw that in where I mean that to be. When should they increase production? They should increase production whenever marginal revenue is more than marginal cost. So at Q1, is marginal revenue greater than marginal cost? Well, let's compare the marginal cost is here, right? Marginal revenue is here. I think marginal revenue is more, right? It's steeper. So yes, since marginal revenue is greater than marginal cost. And we mean slope of revenue, and this is slope of cost. All right, then the last question is, I wonder if it's showing on this page. Yeah. Last question is, should the company increase or decrease production at point Q2? So at point Q2, right, I'm saying it's over here. So here's quantity 2, right? I moved it over a little bit. So at that quantity, they're not going to make a profit until they do more than what? How many? They're not going to turn a profit at all until they get to that inflection point, right? Which is at 130. So they don't have a choice, right? They can't make less because they're not going to make any money until they get to that inflection point. So they have to make more in order to make money at all, right? They don't have a choice. So until they make more than 130. And that Q2 point is it's less than 130. All right, one more example. Any questions so far? This making sense? Good. I really did try to go through the Wiley problems and like kind of know ahead of time what you might have questions on, and I built it into these notes for you guys. So, okay, so the graph of a cost function is given in the figure, just cost this time. Does it cost more to produce the 500th item or the 2000th item? So let's look at that. Let's see, 500 would be right here because these are in thousands, right? So this would be 500. So we're looking at that point, and we want to compare it to the 2000th, which would be here. So cost more, meaning marginal cost, meaning slope, right? So we're going to take a look at the slope right here of a tangent line and take a look at the slope right here. Well, this one is steeper. So we can say that the marginal cost at 500 is greater than the marginal cost at 2000, which makes sense, right? Because if you think about companies making products, remember from economics class, it's called economies of scale, right? So economies of scale is what you use to make more money, right? The more items you make, that means the fixed costs are spread out between more items, right? Okay, so that should make sense. So basically, it costs more to make $500. All right. Does it cost more to produce the 3,000th item or the 4,000th item? So what do you guys think? Just looking at your graph. So we're looking at 3,000 compared to 4,000. Kind of want to draw in like a so which one is steeper?
4,000.
4,000. So we can say that the marginal cost at 4,000 is greater than the marginal cost at, what was the other number? 3,000. So it costs more to produce $4,000th item. All right, and then I think there's one more question. At approximately what production level is marginal cost the smallest? What is it? Yeah, absolutely. It is. And you guys can't see the bottom of this thing, so you can't tell. Yeah, you're looking for something that has a slope that's close to zero. So where does it flatten out? I think it flattens out somewhere around 2,000 or maybe a little bit more than that, right? Somewhere around there, it kind of flattens out, right? So we can say that the slope of the cost function is close to zero when we're talking about a horizontal line, right? When, oops, Q is about what? No, sorry, when Q is, no, that's not what I wanted to say, wait. Sorry. There we go. With a total cost of about what? What are you gonna put in that? So when Q is 2,000, let's say if X was 2,000, what's Y? Approximately. 10,000, right? Yeah, so this lines up with about 2,000, that lines up with about 10,000. We're talking money, right? Dollars. Okay. Anybody have any questions? No? All right. You guys enjoy this beautiful weather. And those of you online, sorry, I will get used to just standing in front of the podium. It's hard for me. Tommy, okay? Oh, guys, y'all are ready. You can go. If anybody wants to set up an appointment with me, you can. I'm going to leave campus right now. But if you want to make an appointment with me, then just email me, okay? Or even better, text me. Way better, because I'll get it faster, all right?
Will do. Have a good
All right.
weekend, Professor.
Thank you. You too, sweetheart. Bye, guys. Thank you. Have a great day. Thank you. See ya. Thank you, guys. You too. Have a great day. Get outside. It's beautiful.